So now that we know computers store information as just zeros and ones, let's talk about how to convert decimal numbers to binary. So in our decimal number system, what does the number 4036 represent and why? It represents different powers of 10, right? When we write the number 4036, we are saying that we have 6 ones, 3 tens, no 100s, and we have 4 1000s. So if we look at this pattern, we have 10 different symbols in our number system, 0 through 9. And so the first digit would be 10 to the 0, which represents 1. So this is the ones column. And then the next would be 10 to the 1, which is the tens column. And then 10 squared, which is the 100s column. And then 10 to the third power would be the thousands column. And we can just keep growing this by adding more place values and then incrementing the exponent, right? The next place value would be 10 to the fourth and then 10 to the fifth. So each place value is a power of 10. And then what the number 4036 represents is the number of those place values. So again, it says that I have 4 1000s, 0 100s, 3 tens, and 6 ones. So that's our number system, right? And when we add those all up, you get 4000 plus 0 plus 30 plus 6. So 4036. So it's the same in binary, but each place is going to be a power of 2 because we only have 2 symbols, 0 and 1. So you're going to pause the video now and make this manipulative using your 8.5 by 11 blank sheet of paper. So I would recommend folding it in half this way and then folding it in half again so that you have 4 rows. And then fold it the other way, this way, and then fold it again and again so that you have 8 different columns. And then unfold it and then write the numbers, the different powers of 2, and on the right hand side this would be 2 to the 0 or the 1's place, 2 to the 1 or the 2's place, 2 squared or the 4's place, and then just continue that out all the way to the 128 place. And then write a row of zeros. So fill in all of those boxes with zeros, turn your paper over, and on the last row, on the back side, not on the front side, write the numbers 1. And then when you cut these, you're just going to cut down like this, and then we can flip them up and flip them down to represent either that bit is going to be a 1 or it's going to be a 0. So go ahead, pause the video, and make your flippy-do. And another version of the flippy-do is a digital flippy-do. And so this is a picture of what it looks like. You can open the digital version by clicking on this link. It'll make a copy for you. And so in this version, we also have the ones column, the twos column, and then we have these check boxes. And when you check a box, it will turn that bit on, and it will tell you what that bit represents. So if I check this box, it turns on the ones bit. If I check this box, it turns on the 8s bit, right? This box turns on the 32 bit, this one the 64 bit, and this one the 128 bit. And just like in our decimal system, I can add up all those numbers to get what this binary number represents in decimal. Okay, so I would do 128 plus 64 plus 32 plus 8 and plus 1. And then that binary number is 111010001. So each place value represents one bit of information, and bit is short for binary digit. And a bit can be either a 0 or a 1. And your flippy-do has 8 bits, which together we call 1 byte. So using your flippy-do, either your paper one or your digital one, represent these decimal numbers in binary. So which bits do you have to turn on so that all of those places add up to 7? And then which bits do you have to turn on so all those places add up to 20? And then convert these binary numbers to decimal. So turn on the bits 1 and 1 here, and then add those all up, and what decimal number does that represent? Pause the slide and do your work and then come back. Okay, let's see if your answers were right. So I'm going to go ahead and turn off all of my bits so that I start with all zeros, and I want to represent the number 7. So I'm going to need the 1 and then the 2 and the 4, because 4 plus 2 plus 1 is 7. And then how am I going to represent 20? Well, I know I'm not going to need a 32, right? That's way too big. So I'm going to start with a 16. And what if I added an 8? That would be way over 20 as well. So 16 and a 4 make a 20, and then I can turn these off, right? So 16 plus 4 is 20. So the binary number for 20 is 0, 0, 0, 1, 0, 1, 0, 0. And even though these bits are turned off, we will just write them because we usually represent binary numbers in groups of 8. So even though they have no meaning, we will just put the zeros there. For converting, we can turn on 0, 0, 0, 1 and then turn on all of these bits and add up all these numbers to get the number 31. So that's interesting. I think I'm seeing a pattern here. 31 is 1 less than the next bit. So I wonder if that holds true every time. Let's turn on that one. And if I add all these up, that's going to equal 63, which happens to be 1 less than the next bit. That's an interesting pattern, and it is true for all of the places. So now you know 2 number systems. You know our decimal number system, which is a base 10, and it has 10 different digits, and you've just learned a new number system called the binary system. And a binary number system is base 2 with only 2 possible different digits. So we can represent the same number in 2 different ways. We can represent the number 23 in decimal to have a 2 and a 3. We're going to have 3 1s and 2 10s, which equals 23. Or we can represent that number using binary. And we can turn on the bits to represent the number 23. And in that case, we would turn on a 16 and a 4 and a 2 and a 1. And so that would represent the number 23.